Binomial distribution function, first of all, has the following characteristics. There are a fixed number of trials, and the fixed number of trials that we have, we call those n. That's the n right here. And each trial is independent of the other. So any time we choose n things from the population, it's considered to be independent of any other n things. That's the idea of sampling with replacement, or having just a very large sample in the real world. The outcomes can be classified into two categories, a success or a failure. Now these days we're kind of shying away from the idea of a success failure because people tend to get a little confused about that, but success failure just means that one thing is what you want it to be and then the other is considered a failure. It's not necessarily a failure, so to speak. So what we're really looking at is the fact that it's two categories. So the two categories that we would have for, say, the radio example that we just looked at, it's a defective or it's a good radio. And our success in that case, we were looking for the defective. So you see what I mean? The success failure thing can kind of be a confusing thing. And the probability of each success must remain constant, and that probability remaining constant is choosing a defective one doesn't influence the defectiveness of another one. And if that was just a random choice, it would be 50-50 choice that they would actually be defective or not. So we would say that that probability would be 0.5. Well, in the real world, there probably be a much smaller probability that we would have defectives, and that's why we have this binomial distribution to help us compute those probabilities versus doing the tree diagram and computing a probability distribution function like we did before. So that's our probability of success. Now, to do the binomial distribution function, we also need to know what this Q is, and this Q is just the complement of that because we have the success failure, right? It's either this or it's that. They're mutually exclusive because of the independence, and so our probabilities are just complements. So Q's probability, the probability of 1 minus P. The X that we're talking about is all of our trials from 0 through the n trials. And if you think about it, X is just the number of successes here. So the P of X, the probability distribution function, the values of the probabilities are told to us by this function. This is just our combination formula, and then the probability raised to the r power or to the x power. One of the books that I use uses r and one of them uses x's. I believe the Triola book actually uses x's, so we'll put the x in there. So the n factorial over x factorial times n minus x factorial, and this is going to tell you what the probability for any random variable is. Now our calculator will do this as well, and our calculator functions we'll go over a little bit later, but it uses the second function variables menu, which is the distributions menu, and there's actually a Bino PDF. So it's Bino meal, I think CD or PDF, sorry, PDF. I think that's what it looks like, and it's the second function of the variables key to get there, and then you have to scroll down to the bottom. I usually use the up arrow key to get there, and it's because it's down toward the bottom, and then we're looking for this, and this inputs the n and the p and the x, and it gives you the same as these probabilities. Or you can compute these probabilities by hand, which can be a little bit tricky. So let's go ahead and take an example here. So our last example, which the defective radios, was binomially distributed, as I was just explaining a second ago. So in that distribution, we had an n being 4 trials, right? There were 4 radios being chosen. The probability that any was defective was half. And our x's is the number of defectives. That's a success, right? So that's what we have. And these x's, these will run from 0 defectives up to all of them being defective, which is 4. So those are our possible values of our random variable. Now remember that if p is 0.5, then q is equal to 1 minus 0.5, or also 0.5. So let's say we wanted to compute that probability distribution function. We wanted to do it using the formula for the binomial distribution here. So we would be able to create this exact same binomial distribution function that we created before just using the formula. So let me show you that. So we have 0, 1, 2, 3, and 4. So for this one we would have n, which is 4 factorial, divided by 0 factorial, and then 4 minus 0 factorial, times, and then the probability of success being 0.5 raised to the 0 power, and then 0.5, the probability of a failure, being raised to the 4 minus 0 power. So that's using just this formula, right? The n factorial is the 4 factorial, the x factorial is the 0 factorial, n minus x, 4 minus 0, and this is all factorial. And then the probability of success, p raised to the x power, that's 0.5 to the 0 power, and then q, 0.5 raised to the 4 minus 0 power. So simplifying this down, this is going to end up with 4 factorial over 4 factorial. Let me change to a different color here so I can write that up here. So 4 factorial over 4 factorial, which any number over itself, doesn't matter if it's factorial or not, is going to equal to 1. Anything raised to the 0 power is also always equal to 1. And this ends up boiling down to just being 0.5 to the 4th power. So that's 1/2 times 1/2 times 1/2, right, times 1/2, or 1/16. So we see that this probability here is the 1/16 that we computed before looking at the sample space. So now let's go on and let's move to the next one. And so this would look like 4 factorial n over 1 factorial, and then 4 minus 1 factorial, and then 0.5 raised to the 1st power, and then q, the probability of a failure, raised to the 4 minus 1 power. So 4 factorial over 1 factorial and times 3 minus, or 4 minus 1, which is 3 factorial. This ends up being 4 times 3 times 2 times 1 in the numerator, and 3 factorial in the denominator is 3 times 2 times 1. These all end up canceling out, which leave 4. Now that 4 is going to get multiplied by 0.5 times, this is going to end up being 3, right? So 0.5 to the 3rd. Well, 0.5 to the 1st times 0.5 to the 3rd, exponents rules say like bases, add your exponents. This is just 0.5 to the 4th power again. So that's 16. So this says 4/16, which is exactly what we saw it as computed in our sample space. Now we had already done for 3 the counts here. Remember that ended up being 4 too. And so this 4 factorial over 3 factorial and 4 minus 3 factorial, this is symmetric to this. So 4 choose 1 versus 4 choose 3, it doesn't matter. They're the same number. That's the 4. And these numbers just spin around too. And because our probabilities are the same for a success and a failure, it means that the probabilities for 1 and 3 are going to be identical to one another, because this is going to be the probability of 0.5 raised to the 3rd power, and then 0.5 raised to the 4 minus 3 power, which ends up being 1, and so that again, the same one. So you see the symmetry here. And then if you take a look at raised to the 4th power, you're going to see that same symmetry, and so you're going to see that the 4th one, if you use the formula, also comes out to 1/16, and that just then leaves us the middle calculation. So this would be n factorial, 4 factorial, and then over 2 factorial, and then 4 minus 2 factorial, and then 0.5 raised to the second power times 0.5 raised to the 4 minus 2 factorial. And of course 4 minus 2 is going to give us 2, and 2 plus 2 is 4, 0.5 to the fourth power. And so again, that's our 16 in the denominator, right? And then 4 factorial, this is 4 times 3 times 2 times 1 over, and then 2 factorial is 2 times 1, and 4 minus 2 is 2, so that's another 2 factorial, another 2 times 1. So 2 times 1 cancels with 2 times 1, the 2 cancels with the 4, and so we end up being 2 times 3 in the numerator, and that's our 6 that we saw before. So we see the exact same distribution function. Now, we should not leave these fractions unreduced as I have here, but I wanted to make sure you saw it in terms of the same counts that we had before. We would reduce this to 1/4 and 1/4, and this one to 3/4, and so we'd have 1/16, 1/4, 3/4, no, not 3/4, sorry, 2 3/8. So we would have 1/16, 1/4, 3, 1, oops, let me change colors here. This is equal to 1/4, as is the other 4/16. And then we also have the 2/16, divide 2, or 16 by 2 and we get 3, and divide 16 by 2 and we get 8. So those would be all the appropriate denotations for our probabilities. All right, so that's creating a binomial probability distribution function from something that we also saw using counting principles to do, and using a tree diagram. So it makes a link between a lot of different things that we have. Now, the next thing that we want to do is we would want to take a look at how to do this with our TI calculator. So I think that I'll probably make a little video on that, because I do not have the capability of doing it on my computer screen, because I don't have an emulator for a TI calculator. So we can do that at a little bit later date. All right, so now using that probability distribution function, so let me just put this back up here again so that we have it on this page and don't have to flip back and forth. So we could have either 0 defectives, or 1 defective, or 2 defectives, or 3 defectives, or 4 defectives. 1/16 is our probability here. 1/4 is our probability for 1. 3/8 is our probability for 2, 1/4 is our probability for 3, and 1/16 again is our probability for 4. So part D of this question says, find the probability of getting 2 or fewer defective in a batch using the PDF BINO-CDF function. Well, we're going to use our probability here to do this. So this is the probability of getting 2 or fewer, so less than or equal to 2 or fewer defectives. So what we would get here is 3/8 plus 1/4 plus 1/16. So that is 6/16. 3/8 is 6/16 plus 4/16, that is our 1/4, and then plus 1/16, and that's going to give us our probability. And 6 plus 4 plus 1 is 11/16, and 11/16 is going to simplify to a decimal, 6875. So 0.6875. And now I'll explain how to use the binomial probability distribution function, but in a video. But for doing it now, what you would need to do is you would need to put in the BINO-CDF, and you would have to put in n, which is equal to 4, comma, the probability of a success, which is equal to 0.5, and then we're looking for a 2. Now this CDF, this is called a cumulative distribution.